Let us look at question number 20, Set 1, Civil Engineering, GATE 2021. The state of stress in a deformable body is shown in the figure. Consider transformation of the stress from the small xy coordinate system to the capital XY coordinate system. The angle theta locating the capital X axis is assumed to be positive when measured from the small x axis in the counterclockwise direction. The absolute magnitude of the shear stress component sigma xy in MPa rounded off to the first decimal place in the xy coordinate system is asked, and the stress element showing the state of stress is shown with the small xy coordinate axis oriented this way and the capital XY coordinate axis oriented about the small x coordinate axis with an angle theta. Students are also encouraged to watch the NPTEL lecture cited below, where this concept is handled in more detail. However, we will be looking at some fundamentals related to stress transformation as we go on to solve this problem. Let us look at some fundamentals related to the stress transformation. Consider a stress element as shown, with the normal stresses applied in the x and y direction to be tensile and the cross shears to be positive. And let this be with respect to a coordinate system small x, small y. If we have to calculate the stresses with respect to a transformed coordinate system, let us say capital X, capital Y, and let this coordinate system be oriented at an angle theta with respect to the small x axis measured in the counterclockwise direction. We know that the stress transformation equations are given as. Similarly, the shear stress can be written as. Further, it is to be noted that in case we require sigma capital YY, we just need to replace these plus signs with a negative sign. As for the sign convention relating to the angle, if our coordinate axis is oriented this way, we can see that the plus z axis would be coming out of the plane of the paper. Hence, any rotation that has its axis parallel to the plus z axis would be considered positive. Hence, all anticlockwise rotations with respect to this coordinate system are considered to be positive, and all clockwise rotations are considered to be negative. Further, as for the shear, if a stress element is applied with a shear and it distorts to this shape, then the shear is considered to be positive. Similarly, if the stress element upon the application of shear distorts this way, then the applied shear is considered to be negative. Hence, in this case, we can see that under the action of tau xy and tau yx, the element would deform this way, and hence we can see that tau xy and tau yx are considered to be positive shears in this case. Further, from moment equilibrium of the stress element, we can see that the couple created by tau xy has to be balanced by the couple created by tau yx. We can see that tau xy is equal to tau yx. Hence, complementary shears are equal and would orient themselves in order to maintain moment equilibrium. Now let us come back to the solution at hand. From the stress element shown here, we can see that sigma xx is nothing but positive 40 MPa since this is tensile. Similarly, sigma yy comes out to be plus 35.6 MPa. Sigma xy is unknown. Sigma capital XX is given to be 120, and we can see that it is a tensile stress and hence it will be positive. And from our discussion regarding the distorted shape of the element, we can see that if our element was initially oriented this way and sigma xy is applied like that, we know that shear stresses would mobilize themselves in order to create moment equilibrium at the rotated state. In such a case, the stress element would get distorted to this shape, and from our previous discussions we can see that this sort of distortion is related to negative shear stresses. Hence we can see that sigma capital XY is minus 50 MPa in this case. Since we have only one unknown, we can use any of the transformation equations that we have discussed earlier in order to find the unknown stress. Let us use transformation equation for sigma capital XX as we saw. It should be noted that sigma xy and tau xy are but the same representations for the shear stress. In order to differentiate between normal stresses and shear stresses, a general convention to indicate shear stresses by tau is used, However, it is to be noted that sigma xy is a perfectly valid representation for the shear stress, and this should not cause any confusion. Further, it can be seen from the figure that this angle is given to be 90 degree and one of the angles is given to be 30 degrees. Hence, it is trivial to calculate that theta in this case is 60 degrees. Upon substitution, we get 120 is equal to this, and again it should be kept in mind that sigma xy and tau xy are but the same stresses. On simplification, we can see that further we know that cos of 120 is nothing but minus sine of 30, which is nothing but minus half. Similarly, sine of 120 is nothing but cos of 30, which is root 3 over 2. Substituting this, we can simplify the expression for sigma xy as minus 37.8 plus 1.1 by root 3 into 2. And on simplification, we get sigma xy as 96.19 MPa. However, in the question, we are expected to round the stress off to the first decimal place and report the absolute value of the stress. Since our stress comes out to be positive, the absolute value and the obtained magnitude is plus 96.2 MPa, and this is our final answer. Thank you.